Okay, coordination chemistry 2 bonding. So let's have a review first. Coordination compounds. A coordination compound is typically consists of a complex ion and a counter ion. So a complex ion contains a central metal cation which is bonded to one or more molecules or ions, and we call those ones as ligands. So these ligands should have at least one unshared pair of valence electrons, because this unshared pair of valence electrons are the one who will be bonded with the metallic cation. Transition metal complexes. Coordinate covalent bond is the bond that is being formed between the metal cations and the ligands, because both electrons in shared pair come from the same atom. So the ligand here, the unshared pair electrons of the nitrogen, will share these electrons to the silver cation to form now the coordination complex. So we have here some common ligands. We have here monodentate ligands. So these monodentate ligands, they donate a single pair of electrons to the metal. While we have here the bidentate ligands. So these bidentate ligands donates two lone pair of electrons. And polydentate ligands, they share more than two lone pairs of electrons. And we have here the structures as well as the coordination number. So we deal most specifically the octahedral. So evidence for electronic structures. So this describes the types of experimental data that give us understanding about the electronic structure of coordination complexes, such as the molecular orbitals, their energy levels, and electron configurations. So these experimental observations have been used to generate the theories of bonding for the compound complexes. So what we are going to deal with in these lessons are from the experimental data that have been observed. So one evidence is the thermodynamic data. So we can determine the stability of coordination complexes by looking at their formation constant. So this formation constant is the equilibrium constant for the reaction leading to the formation of a coordination complex. The greater the formation constant, the more thermodynamically stable the product complex compared to the reactant complex. So we have now the example of the hexa-aqua cupric ion or hexa-aqua copper ion. And we have here a ligand, which is the amine. So in here, the formation constant is more than 1. So the forward reaction is favorable. So amine displaces the uh, previous ligand of the copper ion, which is the water. Another example here is we have the reaction A and reaction B. So as you can see, for the formation constant of the reaction A, which is the ligand amine, and we have here the formation constant of the reaction B for the ethylene diamine. So reaction B has a higher formation constant. So ethylene diamine ligand displaces this ligand amine, because ethylene diamine formation of the tetraethylene diamine nickel complex is greater than reaction A. So reaction B is more favored, or it is more stable than reaction A. So formation constant can be affected by enthalpy and entropy changes. So we have here formation reaction, reaction for the formation of the tri-En nickel from the hexaamine nickel complex. So as you can see here, we have here the enthalpy, which is the negative, entropy, which is positive. So this reaction is more spontaneous, so it is more favored and it is more stable. Okay, so we have what we call chelate effect. So this is the enhanced affinity of a chelating ligand for a metal ion compared to its monodentate ligand counterparts. So this term comes from the Greek word kilos, which means crab. So when a ligand attaches to the metal ion in a manner that forms a ring, then the metal ligand association is found to be more stable. So complexes containing chelate rings are more stable than complexes without rings. So we have here an example. We have here the ligand ethylene diamine, which is a bidentate ligand, and then we have here the amine, which is a monodentate ligand. So as you can see, the complex that forms with the ligand ethylene diamine forms rings. So it's like a crab attaches to a metal. So this ligand with the ethylene diamine, this complex that have the ligand ethylene diamine is 2 times 10 raised to the 9th power times more stable than the complexes with the amine ligand. So we have another evidence of electronics structure. We have here the magnetic susceptibility. So the magnetic properties of complex in terms of unpaired electrons and their magnetic or spin properties are useful in determining structural features in transition metal compounds. So we deal with diamagnetic or paramagnetic complexes. So we can measure magnetic susceptibility with the formula. So we get the magnetic moment. So this magnetic moment is related to its magnetic susceptibility. So a compound can still have a net paramagnetic character because of the large paramagnetic susceptibility of the unpaired electrons. The number of unpaired electrons can be determined by the magnitude of the interactions of the metal compound with a magnetic field. So this is directly the case for 3D transition metals, but not always for 4D or 5D transition metals, whose observed magnetic properties may arise not only from the spin properties of the electrons, but also from the orbital motion of the electrons. So we can, these following values contributes to the magnetic moment. So we have here the spin magnetic moment, and then we have here the orbital angular momentum. So they can contribute to the magnetic moments. Usually, the spin-only moment is sufficient to calculate the magnetic moments. So we do not consider the angular momentum in here. So you have there the formula in getting the magnetic moment. And this is especially for the first transition series. So we use the spin-only moment. Another factor here is we have the electronic spectra. So we have orbital energy levels can be obtained directly from electron spectra. So this is this can be observed with the different colors of the compound complexes. So another one is we have here coordination numbers and molecular shapes. So we can determine electronic structures of the compound complexes with regards to their coordination number and of course their molecular shape. So we have here theories of electronic structures. So we have four. We have valence band theory, crystal field theory. We have here the ligand field theory, and we have here the angular overlap method. So this valence band theory is not commonly used, but the hybrid notation is still common. So we can apply in the compound complexes the hybridization concept of this valence band theory. And then we have here the crystal field theory. This is an electrostatic approach which is used to describe the splitting in metal d orbital energies. But this does not describe bonding. And then we have here the ligand field theory. This is a more complete description of bonding in terms of the electronic energy levels of the frontier orbitals. So this commonly does not include energy of the bonding orbitals. Next one is we have here the angular overlap method. So this is used to estimate the relative magnitude of the orbital energies in a molecular orbital calculation. So this is more on calculating the energies of the different orbitals in a compound complexes. So first we discuss crystal field theory. So this is developed to describe the electronic structure of metal ions in crystals, where they are surrounded by anions that create an electrostatic field with symmetry dependent on the crystal structure. So the energy of the d orbitals of the metal ions are split by electrostatic field. So covalent bonding is not considered because they assume that it doesn't exist in crystals. So their notion is that ionic bond is prevalent in these crystals. We have here a diagram of the crystal field theory. So when the d orbitals of a metal ion are placed in an octahedral field of ligand electron pairs, any electrons in these orbitals are repelled by the field. So as you can see in the diagram, the isolated ion have degenerate orbitals. And when a ligand approaches this isolated ion, the orbitals are being raised in energy. And due to repulsion of electrons, these 5 d orbitals are split into 2 sections. So we have EG set, and then we have here the T2G set. So for the EG set, we have here the orbitals dx square, y square, and then dz square. So they are raised by 0.6 delta O. And then we have here the T2G. We have the orbitals dxy, dxz, dxy, dyz. And they are lowered by 0.4 delta O. And then the delta O, this is the energy difference of these two sections of the orbitals, which are the EG and then the T2G. Okay. So the 3,2G orbitals then have a total energy of negative 0.4 delta O times 3 because we have 3 electrons in this T2G set. It is equals to negative 1.2 delta O. And for the EG set, it is positive 0.6 because it is raised, and times 2 because we have there 2 electrons. So it is equals to positive 1.2 delta O. So the splitting is affected by the nature of the metal ion. And then, of course, the metal's oxidation state. So the higher the oxidation state leads to a larger splitting. So the arrangement of the ligand around the metal ion also affects the splitting of these orbitals. And another one is the nature of the ligand surrounding the metal ion. Okay, so the crystal field stabilization energy, or CFSE, the energy difference between the actual distribution of electrons and that for the hypothetical configuration with all electrons in the uniform or the spherical field level. So this quantifies the energy difference between the electronic configuration due to the d orbitals experiencing an octahedral ligand field that discriminates among the d orbitals. So the d orbitals experiencing a spherical field that would increase their energies uniformly. So the CFT, crystal field theory, successfully accounts for some magnetic properties, the colors, and then the hydration energies of transition metal complexes. But it does not attempt to describe bonding. So as you can see here, we can determine the magnetic properties by looking at the paired and unpaired electrons in each orbitals. So this difference, the delta O or the delta, this implies what colors also for the coordination compounds. So the difference in this delta can predict the color of the compound complex. So what are the drawbacks of crystal field theory? So this does not rationalize the electronic stabilization that is the driving force for metal ligand bond formations. So it does not include lower molecular orbitals. Thus, it fails to provide a complete picture of the electronic structure. So we know that in a bonding, it should involve the valence electrons of the compounds. But in here, for the crystal field theory, they just include or they just focus on the d orbitals. So what about the s and p orbitals? So in a more complete approach for the electronic structures of the compound complexes, we have now what we call the ligand field theory. So this ligand field theory is a combination of the crystal field theory and molecular orbital theory, which we have tackled during the previous lessons. So this ligand field theory is proposed by Griffith and Orgel. Okay, so we have here molecular orbitals for octahedral complex cells. So ligands can interact with metals in sigma fashions. So meaning they are donating electrons directly to the metal orbitals. So this is end-to-end connection. And we have here the pi fashions, which means that ligand metal orbital interactions occurs in two regions off to the side. So the first diagram here or the pictures, as you can see, it is end to end. So these are all sigma fashion. Okay. And then we have here the pi fashion. So we have there a side to side connections or sharing of electrons. Okay, so we have here the sigma interaction in octahedral complexes. So this figure is a sigma donor interaction with metal d orbitals. Okay, so in here, to be able to form a bond between metal and the ligand, the orbitals should be symmetry to each other, or they are the same with each other. So for the M part here, which is the metal, we have here the d orbitals, we have here the Eg, we have here the T2G, and then for the ligand, we have the Eg, TiU, Ag1. So this Ag1, this refers to the S uh, S orbital, and then we have here the TiU. This refers to the p orbitals. So we have there three orbitals for the p, and then we have here the Eg for the d. Okay, so the Eg orbitals on the metal and the Eg orbitals in the ligands, okay, they now form Eg at the middle, as you can see. So we have now the bonding orbitals and then the anti-bonding orbitals. So this is same with the molecular orbital theory. So there is bonding and anti-bonding orbitals formed. Okay, and then for the T2G, for the metals, this is it doesn't, the energy for this T2G is unaffected. So this is because there is no same orbital with the ligands. So there is no bonding that would happen in this T2G. So this is an non-bonding orbitals. Okay. Another here is we have the sigma donor interaction with metal s, p, and then d orbitals. Okay, so the symmetry labels of the atomic orbitals are capitalized. There, the E, T, and the A. And the labels of the molecular orbitals are in the lower case. So the 6-field ligand donor orbitals contribute 12 electrons to the lowest 6 molecular orbitals in this diagram. So the metal valence electrons occupy the T2G and the possibly EG star orbitals. So this lowered orbitals are more ligand in characteristic because these electrons that is in these lowered orbitals or in these bonding orbitals came from the ligands, while for the T2G, the electrons in this T2G came from the metal, and sometimes electrons in this EG star are from the metals. Okay. So this antibonding, this raised energy, raised orbitals are more of the metallic characteristics. Okay, so as you can see, Ag1 is paired with the Ag1 of our ligand donor. And then the TiU are paired to the TiU of the ligand donors. Okay. So we have here a molecular orbital diagram for sigma donor ligands in octahedral complex. So same with the previous diagram. This is more more complete, but they are the same. Okay, so this one in this lowered energy are the bonding. So they are mainly ligands in characters because these electrons are shared or donated or came from the ligand, came from the ligands. Okay, and then this T2G, these are non-bonding, so they are pure metallic because it has no symmetrical, it does not have a symmetry with the ligand. Okay. So the beautiful colors of many transition metal complexes are due in part to the energy difference between the T2G and then the EG star orbitals in these complexes, which is often equal to the energy of photons of visible light. So the difference here in the delta O between the T2G and then the EG star. Okay, so this can be the parameters, or this can be observed to predict what colors of the compound complexes. Okay, so these differences gives different colors of the compound complexes. So we have here the pi interactions. So although sigma bonding can describe energy levels in octahedral compound complexes, we have to modify when ligands engage in pi interactions because it has dramatic effects on the T2G orbitals. So we have there an example, the hexa carbonyl chromium. All right. So in the diagram, we have here the sigma bonding and the pi bonding. Okay. So sigma donor and pi acceptor interactions in an octahedral complex. So that is the diagram. The 6-field ligand donor orbitals contribute 12 electrons to the lowest 6 molecular orbitals in this diagram. So the metal valence electrons occupy the T2G, now the pi bonding orbitals, and possibly the EG star orbitals. So in here, the T2G, this this forms pi bonding. It's not sigma bonding. So this participates in the pi bonding. Okay. So yeah. So pi interactions. Strong pi acceptor ligands have the ability to increase the magnitude of delta O by lowering the energy of the T2G orbitals. Electrons in the lower bonding orbitals are largely concentrated on the ligands. Electrons in the higher levels generally are in orbitals with high metal valence orbital contributions. So this is affected by ligand field effects and determines structural details, magnetic properties, electronic spectrum absorptions, and coordination complex reactivity. So we have here metal to ligand bonding, or sometimes called the back bonding. Okay, so what does this mean? So electrons come from the orbitals of the metal, now occupying now the pi orbitals with contributions from the ligands. Okay, so for example of the diagram, so we have here the carbonyl ligand and we have here a metal. So the carbon has unshared electrons. So these unshared electrons are given to the metal. So they are being shared to the metal. And then this metal, it has filled orbitals also. And then this carbon ligand here has unfilled orbitals. So the electrons in the metals will transfer now or donates back to the carbon ligand, okay, to fill these empty orbitals of our carbon ligand. Okay, so we have here the terms pi acceptor ligands. So these are ligands that have empty orbitals that can engage the metal in pi interactions. And then we have here the pi donor ligands, ligands that donate pi electrons to metal ions. Okay, so the combination of sigma and pi donations from the ligands give the metal more negative charge. So for the figure on top, carbon here is the pi donor ligand because it donates the pi electrons to the metals, while the picture below, carbon here is the pi acceptor ligands because metal ions give back the electron to the carbon ligand. So it is considered a pi acceptor ligand. So this is a back bonding. Okay, so we have here types of ligands. So we have here sigma donor, the pi donating, and then the pi accepting ligands. Okay, so pi accepting, the metal give back or brings back to the ligand the electrons that was donated originally by the ligand to the metal. So forming back bonding. Okay. So we have here examples of donors and acceptor ligands. So you can see we have here sigma donors, we have the amine, water, and hydrogen ions. And then we have here effects of pi bonding on the delta O using a D3 ion. So this is a diagram between cyanide ligand and then the chromium metal ion. Okay. So in the left side, we have here the pi acceptor ligands. So as you can see, the difference of the delta O from the Eg star to the T2G orbitals. And for the pi donor ligands to the right, you can see that T2G is lowered. And then we have here the T2G antibonding. Okay, this is raised. Okay, so we have the difference between the delta O in the pi donor ligands is much smaller than the difference in the pi acceptor ligand. So it is larger in here compared also to the sigma bands only. So pi donor ligands have a smaller energy difference compared to the sigma bands only. And pi acceptor ligands have larger energy difference compared to the sigma bands only and the pi donor ligands. Okay, so we have here orbital splitting and electron spin. So strong field ligands, ligands whose orbitals interact strongly with the metal orbitals. So we have here weak field ligands. We have ligands with weak interactions. So strong ligand field, they have a large delta O, and of course they have a low spin. So as you can see on the diagram below on the right, so the energy difference or the delta O is large, and then it has low spin because this applies the Hans rule. So it would fill first the lowest possible energy before going up to the higher energy, because T2G has lower energy than the EG. So EG in here in the strong field ligands have high energy. So we have to first feel the lower energy before going up to the higher energy. But for the weak field ligand, the diagram at the middle, we have here as high spin complex because it has a small delta O. So this means that T2G and EG orbitals have almost the same energy. So the electrons will fill all these orbitals first, okay, following the Hans rule. Okay, so that is weak field ligand and a strong field ligand. And we have here the D0, D3, D8, D10. Only one electron configuration is possible because we're going to see later on. And then the D4, D7, they exhibit high spin and low spin. So we have here low spin. Okay. So D6, D7, the low spin of D6, D1, D2, D3, D4, D5, D6 until D8. Okay. And then we have here the high spin of D1 to D10. So as you can see, low spin and high spin of D1, D2, D3, D8, D9, and then D10 are all the same, while the electronic configuration of D4, D5, D6, and D7 have two sets. So we have a low spin, and then we have here a high spin. So their low spin are all, we have here paired electrons. Okay. And then for high spin, D4 and D5, they are all paramagnetic, or they have, yes, they are all paramagnetic. And we have here D6, D7, you have also their unpaired electrons, so they are also considered paramagnetic. Okay, so that's it. So orbitals and electron spin. The energy of pairing two electrons depends on the Coulombic energy of repulsion and the quantum mechanical exchange energy. So the delta O, the Coulombic repulsion, and the mechanical exchange energy determines the orbital configuration of the electrons. So if the delta O is greater than the Coulombic energy repulsion, it has a low spin configuration, which is more stable. But if the delta O is lesser than the Coulombic energy repulsion, it has high spin configuration, which is more stable. Okay, so the strength of the ligand metal interaction is greater for metals having higher charges. So an example here is the delta O for 3 plus ions is larger than the 2 plus ions. And metals from the second and third transition series from low spin complexes more readily than metals from the first transition metals. So we have here splitting orbitals, the d orbitals of the different geometrical structures of our compound complexes. So you have their square planar, you have their trigonal, bipyramidal, square pyramidal, you have there the octahedral, pentagonal, bipyramidal, and then the square anti-prismatic. So ligand field stabilization energy, LFSE, the difference, this is the difference between the energy of the T2G over the EG electronic configuration resulting from ligand field splitting. So the hypothetical energy of the T2G over the EG electronic configuration with all 5 orbitals degenerate and equally populated. So this is a traditional way to calculate the stabilization of the d electrons because of the metal ligand environment. So we have here an example. So one electron, the total LFSE is negative 2 over 5 delta O. Okay, and then we have here the high spin 4-electron system. The total LFSE is equals to negative 3,5 delta O plus 3 times negative 2 over 5 delta O, which is equals to negative 3 over 5 delta O. Okay, so how is that? All right, so as you can see, in other books, the delta difference for the EG is referred to as 3/5 of the delta O. Sometimes in the other books, it is 0.6. And then we have here negative 2 over 5, negative 2/5 of delta O for the delta O of T2G. Okay, so some in other books, they refer it to as 0.4. Okay, so one electron, let's go back to the example. So we have here one electron. The total LFC is negative 2.5 because 1 times negative 2.5 is equals to negative 2/5 delta O. And then for the electrons that has a high spin and has a 4 electron, the total LFC is, we have the 3/5 delta O times 3, 2, 4, 5. So, sorry, you have to remove the 1 electron in the EG. So it has at least 4. So in the diagram, you have there 5. Okay. So if we remove this 1 electron in the EG, okay, we have now the 1 electron in the EG. That is why we have here 3/5 delta O. And then we have here plus 3. We have here 3 times the negative 2/5. So we have here 3 electrons in the T2G. So we're going to multiply it by the negative 2/5 delta O to get the total LFC of a 4 electron system. So please remove that one. 1 electron in the EG. Sorry. All right. So we have now the square planar complexes. So since there are no ligands along the z-axis, the repulsion of electrons in the dxz, the dyz, and then the dz square orbitals are considerably lower than that of the octahedral complex. So the dz square orbital is slightly higher in energy to the donut that lies on the xy axis. So in square planar complexes, you have this structure. So in square planar complexes, the delta will almost always be large, even with a weak ligand. So electrons tends to be paired rather than unpaired because pairing energy is usually much less than delta. So therefore, square planar complexes are usually low spins. Okay, so square planar have large delta and then they are usually low spin. So we have here the pi interaction of our square planar. Okay, so you have there the bonding orbitals. We have here the anti-bonding orbitals. Okay, and then we have here the non-bonding orbitals. And you have the other diagram for this orbital bonding pi interactions. Okay, so that's it. So for this one, for this figure, this is D4H molecular orbitals. This includes the pi orbitals, pi orbital interactions with metal d orbitals that are indicated by solid lines. Okay, and interactions with s and p orbitals are by dashed lines, and non-bonding orbitals are dotted lines. So this is a combination of a pi orbital and a sigma orbital. And so as you can see, it is so complex. So the orbitals should always be symmetrical to the orbitals of the metal and then the orbitals of the ligands. So if it's not symmetrical, there is no bonding that will be formed. Okay, so we have here the tetrahedral geometry or tetrahedral geometry. So for the tetrahedral geometry it is analogous to a pyramid. So where each of corners of the pyramid corresponds to a ligand, and the central molecule is in the middle of the pyramid. So in a tetrahedral complex, the delta T or the delta tetrahedral is relatively small even with strong field ligands, as there are fewer ligands to bond with. So it is rare for the delta T of tetrahedral complexes to exceed the pairing energy. So as you can see there, okay, so as you can observe, for the octahedral, Eg is on top or it is being raised in energy. But in here, in tetrahedral field, T2G are being raised in energy. And then the Eg are lowered in energy. Okay. So the crystal field theory diagram for tetrahedral complexes has dx square, y square, and dz square orbitals equally low in energy because they are between the ligand axis and experience little repulsion. And then electrons will move up to the higher energy orbitals rather than pair. Because of this, most tetrahedral complexes are high spin. So common for complexes where the metal has D0 or D10 electron configuration. So this is more common to D0 or D10 electron configurations. So we have here an example. We have there the CH4 ligand. Okay, so we have here the molecular orbitals for tetrahedral. We have here the tetracarbonyl nickel. Okay. So LUMO is the ligand LUMO is the ligand unbonding molecular orbital, and then the HOMO is the higher orbital yan. So if delta E is greater than P pairing, then the complex will be square planar. But if the delta E, the energy, is less than the pairing, and then the complex will be tetrahedral. So we have here an example. The molecules PdCl4 is diamagnetic, which indicates a square planar geometry, as all 8d electrons are paired in the lower energy orbitals. So however, nickel Cl4 is also D8 but has two unpaired electrons, indicating a tetrahedral geometry. So why is that PdCl4 is square planar if chlorine ion is not a strong field ligand? So as you can see, we have here metal PD and then we have here the metal nickel. So this depends on the metallic ion. So one factor that can um, give us the electronic structure or the structure of these compound complexes, we can determine on the metallic ions. So here you have there the structures of our two complexes. All right. So you have their tetrahedral and then the square planar. So as you can see for the orbitals, you have there the EG, T2G of the octahedral, and then there is repulsion of the electrons. So the dx square, y square are being raised, while the dxy is lowered, and then dz square is also higher than the dxz and then the dyz for our square planar. All right. So we have here the molecular orbital for our tetragonal and square planar compared to our octahedral. So as you can see, square planar has really a large delta difference compared to tetragonal. So we have here the angular overlap. So this is a useful approach for making estimates of orbital energies in coordination complexes. So while having the flexibility to deal with a variety of geometries and ligands. So this estimates the strength of interaction between individual ligand orbitals and metal d orbitals based on their mutual overlap. So the term angular overlap is used because the amount of overlap depends strongly on the angular arrangement of the metal orbitals and the angles at which the ligand interacts with metal orbitals. So this is more focuses on the metal d orbitals. Okay, so angular overlap is it's more on calculations on the energy levels of the d orbitals. So this angular overlap can determine the stability of the structure of the compound complexes based on the computed energy differences between those or the sum energies of those d orbitals. But calculations for this one are so broad, so we're not going to go with the computations. So let's have just the concept. So in here, the sigma donor interactions and the angular overlap, you have there the diagram. The strongest sigma interaction is between the metal dz square orbital and a ligand p orbital. Okay. So dz square is has more energy than the sigma orbital of our ligands. Okay, so you have there the complex, we have the E sigma, and then you have there the E sigma higher. So for the pi interactions in angular overlap, the strongest pi interaction is defined as between a metal DXA orbital and a ligand pi star orbital. So the antibonding molecular orbitals with high contributions from the ligand pi star are higher in energy than the original pi acceptor ligand orbitals. So molecular orbitals with high ligand pi donor orbital character are lowered in energy. So you have here the diagram of the simplified molecular energy level diagram for a hexacarbonyl chromium. Note that the empty pi star orbitals there at the top, and then we have only three are involved in the overlap with metal d orbitals. Okay, so we have here the T2G. So we have here the three orbitals involved in our overlapping. Okay. So we have here a spectrochemical series. A spectrochemical series gives the arrangement of ligands in order of increasing crystals field splitting. So remember, if it has a weak field ligands, the difference, the delta difference is smaller, or the splitting is small. While if you have a strong field ligands, the delta difference is large, or the splitting is large. So ligands before water, such as the iodine ions and O3, OH, are weak ligand fields, are weak field ligands, while ligands after the water are strong field ligands. So strong field ligands cause greater field splitting, and then other factors which affect the crystal field splitting depends on what type of ligand is being associated with the metallic cation. All right, so we have here the John-Taylor effect. So this is sometimes also known as John-Taylor distortion. This describes the geometric distortion of molecules and ions that is associated with certain electron configurations. So this is an electronic effect. This electronic effect is named after Hermann Arthur John and Edward Taylor, who proved using group theory that orbitally degenerate molecules cannot be stable. So this John-Taylor effect states that any nonlinear molecule with a spatially degenerate electron ground state will undergo a geometrical distortion that removes the degeneracy, because the distortion lowers the overall energy of the molecule. Right. So we have here that John-Taylor distortion of a D9 octahedral transition metal complex. So the tetragonal distortion lengthens the bands along the z-axis as the band in the xy plane become shorter. All right, so this change lowers the overall energy because the two electrons in the dz square orbital go down in energy as the one electron in the dx square y square orbital. So in here there is an elongation and the opposite of elongation. That's sure. All right. So this elongation minimize the repulsion of the electrons. That's why the structure of the transition metal complex is being distorted. So we have here degenerate orbitals in the red box here. This is unequally occupied. So it requires a John Taylor distortion. So they are not symmetrically fit, or they are not symmetrical. So um, they will have a distortion so that they will minimize repulsions. And then we have here the D4H. For the D4H, it has a compressed, it becomes shorter. The axis or the bond is become shorter. Okay, and then you have there the octahedral, and then elongated. You have there the elongation of the z-axis. It's more on the z-axis that will elongate to distort the structure. All right, so we have here a summary. Okay, so D1, for D1, we have compression. T2, it will undergo elongation. But for D3, there is no distortions because they are all symmetrical. And then D4, low spin, it will undergo compression. And then D4, high spin, okay, it must distort but cannot specify whether it is elongated or compressed. So for D5, we have here low spin, so it will undergo elongation because they are not symmetrical. And then for D5, high spin, they are all unpaired electrons. So there is no distortion in here because they're all symmetrical. Okay. So you have there the D6 also do not undergo John Taylor distortion. For D6 high spin, you have their compression. Okay. So D8, D10, they don't undergo John Taylor distortion. Okay. So we have here 4 and 6 coordinate preferences. So we have square planar versus octahedral. So only the D8, D9, the D10 low spin complexes find this geometry energetically favorable. And then square planar versus tetrahedral, we have there the D0, D1, D square, D10 complexes with the strong field ligands. They prefer the tetrahedral shape. While for the D5, D6, and then D7 energies, their energies are the same for weak field cases. Okay, so you have their distortions by the John Taylor effect. Okay, so we have there the octahedral and then tetragonally distorted octahedral field. So and square planar. So we can also determine which is more stable structure. Is it the tetrahedral? Is it the square planar with weak field, or square planar strong field, using a diagram? So you can have this diagram in here. Yeah. So other shapes, we have here the trigonal bipyramidal case of 5 coordinate complexes, or the D3H. So in this one, the group theory and then the angular overlap can also be used to determine the orbital interact with ligand sigma orbitals and to approximate the relative energies of the resulting molecular orbitals for a wide variety of geometries. So you have there the structure or the shape, structural shape of our bipyramidal. Okay. So this is my reference, and thank you for listening. I hope you learned something for this video.